We're going to start now with our talk about storage elements. Those will be latches and flip-flops, and they create memory. Right? So a storage element in a digital circuit can maintain a binary state indefinitely, as long as power is delivered to the circuit until it's directed by some sort of input signal to switch states. Our states are going to be zeros and ones. The major differences among various types of storage elements are in the number of inputs they possess and the manner in which the inputs affect the binary state. Storage elements that operate with signal levels, so a level is a 0 or a 1, rather than signal transitions. Transitions are when a signal rises from 0 to 1 or falls from 1 to 0. So level signals are referred to latches. We'll see that a latch is controlled by the level, a 0 or 1, and not a rise and a fall. Those controlled by a transition are called flip-flops. So we'll say that latches are level-sensitive devices. Flip-flops are edge-sensitive, a clock edge, rising or falling clock edge. Latches implement a simple form of memory by introducing feedback. Right? In the previous lecture, we looked at a simple circuit, an oscillator, well, a NOT gate that had feedback to its input. So the gate output is wired to a gate input. It doesn't have to be its own gate. It could be another gate within the circuit. We'll take a look, then we're going to develop a gated transparent D latch and see that that is a level sensitive device. The latch's D input will store whatever value is present on the input. When the clock signals high, it's going to remember that value when the clock signal transitions to low. So it'll be a level sensitive, that when the clock level is high, whatever's sitting on the input will be latched into memory. It will stay there while the clock signal is low. What it does is it does create a problem of when the output of one latch propagates to the input of another latch. So as we start chaining these together, chaining latches together and controlling when the signal changes on them, since they're level sensitive and the level can occur over a certain amount of time, actually doesn't allow us to control the circuit's timing very well. So we'll see that latches are actually used in hardware to store information, like your keyboard uses latches to store information about what key you actually just hit. But flip-flops then, they're going to store input, but they'll store input on a shorter time period on the clock edge. They'll hold that value until the next clock edge. And so it's much easier to control timing with flip-flops. When we talk about present state, we're going to start using Q to represent state. So present state means the state of Q output at the time the input signals are applied. So Q at time t, Q the present state. The next state is the state of Q's output after a latch or a flip-flop has reacted to the input signals. That's denoted as Q at time t plus delta t. So sometime afterwards. Present state, sometime after that state, next state. Right. Delta t is the time required for the change of state to occur. Like I said, we're going to be concerned only with the state of the latch or a flip-flop, only when the outputs are stable. So we'll only look at those at times t and t plus delta t. Right? We won't look at them in between times. We have to control our timing. Right. So what is a latch? Right. There are different types of latches. We'll take a look first at a set reset, an SR latch, and then a data latch. So the SR latch can be built with NOR gates, NAND gates. It's called SR set and reset. Right. So here is an example that is built with NOR gates. We have two inputs. Right. S is for set, R is for reset. The latch has two useful output states. The set state, we'll see the output is actually a 1. The reset state is a 0. These are seldom used in practice because they have indeterminate states. And so there's a combination of inputs you should never assert on these. So let's take a look now. Right. Both inputs of the latch remain at 0 unless the state has to be changed. So what this is talking about is this is defining the behavior of the SR latch. So the SR latch should remain at 0 unless the state has to be changed. The application of a momentary 1 into the S input causes the latch to go into the set state. The S input must go back to 0 before any other changes take place in order to avoid the occurrence of an undefined next state that results from the forbidden input condition. Right, here's our logic diagram. Right out here, this is just a signal level going from 0 to 1, showing that these could be possible inputs to the latch. And what we want coming out of the latch is we have to then adhere to the condition that we have these two outputs. We have Q and Q naught. And the condition we have to adhere to is that Q naught will always be the inverse of Q. And here's what we call the function table for the latch. All right, let's look at the first line. When S is a 1 and R is a 0. So this refers to that application of a momentary 1 to the S input causes the latch to go to the set state. And the set state is a 1 state. So when S is a 1 and R is a 0, the output of the latch Q is a 1. If Q is a 1, the Q naught has to be the inverse of that. It has to be 0. Now, before we then allow any other inputs to come through, we have to change the state back to 0, 0. Right? So after S is a 1 and R is a 0, we change the S back to 0. When we do that, it holds its state. Q then still remains a 1, Q naught remains a 0. So we've set the output of the latch to a state of 1. Otherwise, the other state is a 0, right? When S is a 0 and R is a 1, so R stands for reset state. So when R is a 1, then Q is a 0. So reset means reset the output to 0. And of course, Q inverse then has to be the opposite of Q. If Q is a 0, Q inverse has to be a 1. And then our condition for using the SR latch says we have to then make the R go back to a 0, so the input sitting on the latch has to be 0, 0. The output Q then remains a 0, so it remains in the reset state. So we can think of these 0, 0 states as hold states because the latch will hold whatever its output is. But we also have a forbidden state. We can never assert both a 1 on S and R at the same time. When we do that, because of the feedback in this circuit, Q becomes a 0 and Q naught becomes a 0. And that violates our condition that Q naught is the inverse of Q. So if we use an SR latch, we have to control our inputs to make sure there's never a time, right, when both inputs are 1 and our outputs, Q and Q naught, would be incorrect. All right, and so these slides in your lecture notes go through what I was just talking about. What happens when we apply a 1 to both, right? It produces an undefined state. And so that violates our requirement. So when these are both 1s, that violates this requirement. You can read through these in your lecture notes, right? So here's our function table, right? Here's the function table here. This is still, again, the function table. All I did was went ahead and assigned the names here. Here we just show the outputs, right? Here it might help you to remember states. The set state, Q in the next state will always be a 1. So this Q plus is another way of saying next state. We usually say Q plus instead of T plus delta T. So Q in the, so when your input, your present state input sitting there is a 1 for S, 0 for reset, then your next state then of your latch will be a 1. So set means set the output to 1. Reset means reset the output to 0. The 0 zeros are no change states. So no change are sometimes called hold states. So when that signal is asserted, right, the output on Q does not change. And then we have this forbidden state, right? So that's the characteristic of a NOR gate function table. And we can write things in terms of a state table. So the function table looked a bit like, it looks a little bit like a truth table, except, right, we have more input combinations here than 4. Some are repeating simply because there are no change states. When we start working with sequential circuits, we start working with state tables. We're going to see that state tables are very much like truth tables. So we have the present state inputs. We have S at time t, so S is the present state. R of time t, R of the present state, right? Q of t. So Q, remember Q is the latch output, but if we have feedback into our system, Q becomes a present state input. So all three of these, SR and Q, are present state inputs to our circuit. And what this is saying then is our output here. So in your truth table, right, our outputs we labeled F, G, H. Here, this is Q in the next state, Q at T plus delta T. Like I said, we often shorten it up to be Q plus instead of saying the T plus delta T. But let's take a look, right? So here we've got three inputs. We know that 2 cubed is 8. So we've got all 8 possible binary combinations here on this present state set of inputs. For our state table, you can think of a state table as a truth table. The odd thing is the output of your sequential circuit becomes an input on the present state. That's the difference. All right, so when S is a 0, R is a 0, right, we said that's a no change state. And so if Q in the present state is a 0, then Q in the next state will also be a 0, because when S is 0 and R is 0, that's the no change state. Likewise, here when S is 0 and R is 0, and Q in the present state is a 1, Q in the next state will also be a 1, because that's the no change state. Now, when S is a 0 and R is a 1, remember that's the reset state. So Q in the present time is a 0. Well, we don't really care. The circuit doesn't depend on what Q in the present state is, because whenever we have reset asserted, then Q in the next state will always be a 0. You can see here when S is a 0 and R is a 1, so reset, and Q in the present state is a 1, well, Q in the next state will be a 0, because this combination of S and R produces the reset. So the next state value of Q will always be a 0, no matter what Q is in the present state. Here, when S is a 1 and R is a 0, well, we know that's the set state, and the set state produces a 1 in the next state. And so even though the Q in the present state is a 0, in the next state it will be a 1, because we defined the functional behavior of the set state when S is a 1, R is a 0, to produce a 1 on the output Q. Similarly here, when we have this combination where S is a 1, R is a 0, our output in our present state, Q is a 1, well, our next state, Q, will be a 1. And then here, because these are forbidden states, we're not showing any sort of output for Q, because we're going to assume that we're going to assert control in a way where we will never have these two sets of inputs. So S being a 1 in the present, R being a 1 in the present at the same time. Right? So we just don't show any output there, because that's our forbidden state. Now, we could solve this state table. So here, this next state, when we talk about state tables, that's your output. So your next state, you're going to solve for a next state equation based on your present state inputs. We're going to use then this forbidden state. We could actually put X here for don't cares, because we're going to say we never enter that. So we're going to represent these two outputs with X's. And so that's where this slide comes from. So again, here are our present state inputs. Here's our next state. And so you can see here for a binary input combination 0, 0, 0. So here I've got S of T up here. When S is a 0, that's this column. When S is a 1, that's this column. And R and Q of T. So here is my 0, 0, 0. That's a 0. Here is my 0, 0, 1. 0, 0, 1 is a 1. 0, 1, 0. 0, 1, 0 is a 0. 0, 1, 1. So here's 0, 1, 1. That's a 0. Right. Likewise, now when S is a 1, this half of the truth table, when S is a 1 and R and Q are zeros, S is a 1, R and Q are zeros, we have a 1 here. Right. S is a 1, R and Q are 0, 1, we have a 1. And then the last two, we have the don't cares. We use a K-map here to solve this equation. So we had a group of 4 and a group of 2 where we solve for the 1s. And so we say that the next state equation, which is also called the characteristic equation, the characteristic equation of this SR latch is Q in the next state. So Q at T plus delta T is equal to S in the present state plus R naught and with in the present state and with Q, right? So S in the present state, well, that comes from this column where S is all ones. R naught and with Q, well, S drops out of this group of two. R is a 0, so we say R naught. Q is a 1, so we say Q. And we start dropping these functions of time. We simply write the equation as Q plus, Q in the next state is equal to S ORed with R naught and with Q. Like I said, we assume that SR never equals 1, 1, allowing us to use those don't cares. So that's how we develop then the characteristic equation for an SR latch made out of NOR gates. Now, if we were to make the SR latch out of NAND gates, it has a different forbidden state because of the behavior of the NAND gates. So instead of the no change state that we had as 0, 0 for the NOR gates, for the NAND gates, we're going to have the no change or hold state with both of these inputs being ones. Right? This is still going to function like the set reset latch. So when S is a 1 and R is a 0, then, because of the NAND relationship, Q is a 0 and Q naught is a 1. Then we have to transition to both of these inputs being a 1 in order for this to hold. And then we can transition over to the reset state. Remember, NAND is the inverse. So we have S then being a 0, R being a 1. In this case, then we've inverted the output. The reset inversion becomes a 1. This gets to be a bit confusing, and I don't spend time on the NAND logic because typically the SR latch, when we work with it, we're going to work with the NOR gate form. We're going to work with this functional table. But we're not going to spend time looking at the NAND gate. As a matter of fact, as what we just said, the SR latch is fairly never used. We want to use it as a basis for creating another circuit. So let's just, if you follow through, this does the same thing of developing the next state table, solving for the characteristic equation. But what we want to do is, let's take a look at the SR latch if we actually then add a control enable input to that. In this case, here was the SR latch with the NAND gates. We add another layer of NAND gates. So back here, right, we just had this one layer of NAND gates. Here, what we're going to do is we said, what happens if we add on this other layer of NAND gates? We also added an enable switch into here. What we see then for the behavior of the set reset latch is we define this functional behavior to be whenever enables a 0, there's going to be no change on the output of Q, right? The circuit will be disabled. And if you look at this, well, this input 0, when you have 0 ANDed with anything here, so 0 ANDed with anything gives you a 0, but then when you invert that, that gives you a 1. And with here, you have the enable when it's a 0 coming in here, and with anything gives you a 0, but when that's inverted, gives you a 1, so it gives you a 1 there on the input and a 1 there on the input. Depending on then what your outputs are here, right? This one is going to feed back to the input here. This one feeds back to the input here. And you will see then, if you work through these, that they will actually then end up holding their state. Q and Q naught will not change, right? Whenever the circuit's enabled, so whenever enable is a 1, then you're going to get the set reset behavior of when S and R are both 0s, there's no change. When R is a 1 and S is a 0, we get this reset state. Right? When S is a 1, R is a 0, we get the set state. And then we have this indeterminate, which is also this forbidden state that we would never have all three of these being the same signal at once. So we added some complexity here to the circuit. Right? We still have this indeterminate forbidden state that we can't use. So like I said, we rarely use these SR latches, but as we develop this, we're heading toward a D latch, which is a bit more usable. right, so we'll talk about the D latch, the data latch, in our next lecture segment.